Okay, let's take a look at question 21.42. So it says we're starting it with cyclopentanone. As your starting material and using any other reagents of your choice, propose an efficient synthesis for each of the following compounds. Well, we went over the first one before the break, and we said, well, we've got a 1,5-dicarbonyl, and cyclopentanone is not going to give us a 1,4 addition. So we would have to make the enamine from it. So that means we're going to have this enamine. And of course, we can make that from dimethylamine. And then as far as our Michael acceptor is going to be, so if you look at all of this portion, so I'll put it in green. If I circle all of this, that would be our Michael acceptor. And so it's going to look something like this. That would be our Michael acceptor in this case. So how do we put that all together? We're going to start it with our cyclopentanone. And in step one, we're going to treat it with dimethylamine, a catalytic amount of acid, and we remove water. That forms the enamine. So then we throw in the Michael acceptor, which is going to be this alpha beta unsaturated ketone. Then the last step is we treat that with H3O plus, and we cook that up, and that is going to give us the product. Okay, that will give us the product like that. And again, this is a stork. So we here stork enamine synthesis. And for the last one, it's going to require an aldol addition. It's going to be a crossed aldol reaction because we need to make a bond between carbons 2 and 3. And keep in mind, our starting material is going to be cyclopentanone. So how would we deprotonate that completely to make the enolate? Well, we need something like LDA. You know, I'll just write it out here. So LDA, lithium diisopropyl amide, and that's going to give us the enolate like that. And then our electrophile in this case is going to be benzaldehyde. So if I just draw benzaldehyde like this, then what's going to happen is we're going to get a nucleophilic attack by our enolate onto our electrophile like this. And then we're going to end up with this intermediate. So here's our intermediate, which is going to look like this. So we're going to have a negative charge on our oxygen like this. So then to make the product, all we have to do is throw in methyl iodide as the last step. And then that's just going to do an SN2. Not my best. Let's try again. Try it this way. There we go. Nucleophilic attack, loss of leaving group, and that is going to give us the product. So we're basically throwing in the iodomethane or methyl iodide at the end. So overall, it's a total of 3 steps. Step 1 is LDA. Step 2 is benzaldehyde, so that's this compound. And step 3 is treated with aqueous acid, aqueous acid, sugar, is to treat it with iodomethane. Okay, and that's going to do the SN2 to make the methyl ether at the end. There we go. So this one is a crossed aldol, so crossed aldol. I guess I'd already written that, but any crossed aldol reaction. All right, let's take a look at the last two, these ones here. So these ones, you can see that you have, if you imagine, or this is your carbonyl, so you're adding something at the alpha and the beta carbon. So what they want you to do is add the beta first, okay? So step 1, so we'll do step 1. We'll do Michael addition, Michael. And then step 2 is going to be just an alkylation. So let me show you what I mean. So what we're going to do is we're going to do a Michael reaction to add the methyl group at the beta carbon of the first one. So for that, we're going to start out with the alpha beta unsaturated ketone, like that. And we're going to treat it with lithium dimethyl cuprate. So we're going to use lithium dimethyl cuprate. And I'm not going to draw the mechanism, but that's going to give you this intermediate, right? After it does the nucleophilic attack, we're going to end up with this. And so in the last step, to put in the phenyl, we just use benzyl bromide. And so that's going to do the SN2 like that. And that is going to give us the final product. All right. So for the very last one, it's in a similar vein. we need to add a methyl group here and a methyl group here, and then we could just reduce this to an alcohol using lithium aluminum hydride. So we're going to start out with, let me see here. Let me just write down the steps in order. So step one, so if we take the starting material, come on. So if we take the starting material, and in step one, we do, so we need two methyl groups. So we'll use lithium dimethyl cuprate in the first one. And then in step two, we use iodomethane. Then we're going to have this compound. So we're going to have the cyclohexane ring. We've got the aldehyde. And then we've got the methyl group here and the methyl group here, right? We added a methyl group at the alpha carbon and at the beta carbon. And so to convert it into the alcohol, we could use sodium borohydride or lithium aluminum hydride. Let's use sodium borohydride. We don't use it a lot. So sodium borohydride, and we'll use methanol as our solvent, and that is going to give you the product like that.